In this video, we will see ball milling method. Ball milling method is a top-down approach which comes under synthesis of nanomaterials. Before going directly to the ball milling method, we will see the very brief introduction regarding the approaches for nanoparticle synthesis. Then we will move to the ball milling method. There are two approaches for the synthesis of nanomaterials. Those two are top-down approach and bottom-up approach. Top-down approach is taking the bulk material and cutting that bulk material or reducing the size of that bulk material to small size. What we want is top-down approach. Whereas bottom-up approach is building what we want to assemble it from building blocks, that is atom by atom, molecule by molecule or cluster by cluster. That is what bottom-up approach. Top-down approach involves breaking down bulk materials into nanoscale structures using either physical or mechanical means. And this method starts with a larger structure and systematically it reduces its size to the nanoscale. And often through these certain techniques like mechanical milling, lithography, laser ablation and etching. Coming to the advantages of top-down approach, it is a well-established technique, especially in the semiconductor industry. And it is this top-down approach is suitable for producing large quantities of nanostructured materials, better control over size, over the shape and pattern of the structures at the micro scale. And there are certain challenges, of course, there are advantages, but certain challenges are also there. The main challenge is potential for defects or damage in the final nanostructures, limited control over atomic level precision, and high energy consumption and costly equipment in some methods we need to have in top-down approaches. And it is less effective for producing extremely small nanoparticles. That is also another challenge in top-down approach. Examples for top-down approach are in electronics. Microprocessors are fabricated using top-down lithographic techniques to etch circuits with nanoscale precision. Coming to the bottom-up approach, in contrast to top-down approach, the bottom-up approach builds nanomaterials atom by atom or molecule by molecule through chemical or biological process. And this method mimics a natural process, assembling nanostructures from basic building blocks. And common techniques include in this bottom-up approach are sol-gel synthesis, chemical vapor deposition, then biological synthesis, precipitation and hydrothermal methods or solvothermal methods. These are all bottom-up approach methods. Advantages of bottom-up approach are greater control over composition and structure at the atomic and molecular level, and often it requires less energy compared to the top-down method, and it enables the synthesis of highly uniform nanoparticles with tailored properties. With this bottom-up approach we can get uniform nanoparticles. That is the most one of the important advantage of bottom-up approach. And it is suitable for producing quantum dots, nanowires and other precise nanostructures. And there are also certain challenges in this bottom-up approach. That is difficult to scale up for mass production in some cases. That is, large production is somewhat difficult compared to the top-down approach. And it is potential for aggregation or poor stability of nanoparticles. And another important challenge is it requires stringent control of reaction parameters like temperature, pH and then concentration. And examples for this bottom up approach: gold nanoparticles. They are synthesized via chemical reduction of gold salts in a solution, and this is widely used technique in medical diagnostics and drug delivery systems. So this is the some top down approach, bottom up approach. Okay, advantages, so we already discussed, and now we will move to the ball milling method. So ball milling method is widely used top down approach, and it's a mechanical technique for synthesizing nanomaterials and to reduce the size of the. Here, bulk materials are broken down into nanoscale structures through certain mechanical force. And this technique is extensively employed in material science and also in metallurgy and pharmaceuticals and nanotechnology. So, why it is being used or why it is extensively being employed in material science, metallurgy, pharmaceuticals, and nanotechnology are due to its simplicity, scalability, and cost effectiveness. So, what is this method? Ball milling method is used, of course, for the production of nanomaterials, and this process is used in producing metallic as well as ceramic nanomaterials. And these mills are equipped with grinding media. So, what is that grinding media? Is nothing but it consists of wolfram carbide or steel balls. So, ball mills rotate around a horizontal axis, partially, which is partially filled with the material to be grind plus the grinding medium. So, in the next slides, we will see in detail about this ball milling technique. And the principle behind this ball milling technique is it operates on the principle of impact and attrition. That is nothing but attrition is friction or pressure that we are creating. So, we will take a rotating cylindrical chamber that is known as ball mill, contains grinding media. So, that grinding media typically it is steel or ceramic or tungsten carbide balls. And along with this grinding media, the material which we want to grind also we will take in that cylindrical chamber. So, as the chamber rotates, the balls are lifted by centrifugal force and then they fall back. So, when they fall back, they strike the material with considerable force. So, this is going to repeat many times so that the impact and friction between balls and the material lead to size reduction and the creation of fine powders finally we may get. So, that is the principle of ball milling method. So, here you can clearly observe this figure. So, this is a cylindrical container or a jar, and in this the balls rotate with high energy inside a container, and then they fall on the solid. So, this solid is nothing but which we want to grind, which we want to make it into powder. So, these balls they fall on this solid or on that bulk material with the gravity force and kinetics, and hence they crush the solid into nanocrystalline powders. So, coming to the types of ball mills, there are several types of ball mills used depending on the purpose and scale. So, those different types of ball mills: planetary ball mill, vibratory ball mill, attritor mill, then tumbling ball mill. Planetary ball mill offers high energy input and it is ideal for producing nanoparticles. Multiple jars in this they rotate on both their own axis and around a central axis. So that is planetary ball mill. Whereas vibratory ball mill it uses vibrational energy for milling. and it is often employed for fine powders. If we want to have a fine powder, we have to go with the vibratory ball mill. Then attritor mill, that is also known as a stirred ball mill. It has a stationary tank filled with grinding media and a rotating agitator which stirs the media and material. And fourth one is a tumbling ball mill. It's a conventional ball mill where rotation causes the grinding media to cascade. And coming to the use of ball milling, it generates curved or closed shell carbon nanostructures, carbon scrolls by ball milling of graphite, and nanoporous carbon by ball milling. Then carbon nanotubes and carbon microspheres by high energy ball milling of graphite. And this is the construction of cylindrical jar or ball milling method equipment. A ball mill consists of a hollow cylindrical shell rotating about its axis. Here you can clearly observe. So how it rotates along the horizontal axis, and then how it creates the centrifugal force. The axis of the shell may be either horizontal or at a small angle to the horizontal, that it is partially filled with balls. So the grinding media is the balls, which may be of we already discussed, steel, stainless steel or rubber. And inner surface of the cylindrical shell is usually lined with the abrasion resistant material such as manganese steel or rubber. The length of the mill is approximately equal to its diameter. So these are certain illustrations for ball mill equipment. Then coming to the process parameters that affect ball milling method. So certain factors definitely affect the milling process. So the most important factor is the milling time. Longer times generally lead to finer particles, though excessive milling can introduce impurities or defects. And ball to powder ratio is another parameter which affects milling. A higher ratio can increase the energy transferred to the material. And speed of rotation also influences milling process. Too slow or too fast, both are they may reduce the efficiency or cause unnecessary wear. And then type and size of balls. It affects the impact energy. Smaller balls are better for fine grinding. And coming to the atmosphere, milling can be done in air, vacuum or inert gas to prevent. And these are the advantages of ball milling method. It is simple and cost effective process, and it is scalable for industrial use, and versatility in material types, that is it can be used with a wide range of materials including metal, ceramics, polymers and even biological substances. And production of nanostructured materials is possible with this ball milling. So ball milling is effective in producing nanoparticles and nanocrystalline materials with controlled particle size and morphology. Then homogeneous mixing and alloying. It allows for uniform mixing of different materials, and then it is widely used for creating metal alloys and composite materials. And another advantage is environmentally friendly, solvent free. We are not going to use any solvent in this ball mill method. In many cases, ball milling can be carried out without the use of solvents. So that makes it greener alternative compared to wet chemical synthesis methods. Then customization of milling conditions, milling time, speed, ball to powder ratio and milling atmosphere, they can be adjusted to tailor the final product's properties based on the final product that we want. So we can adjust these parameters and we can customize these parameters and then we can get what the powder we want. Generation of amorphous phases. In certain cases, ball milling can disrupt crystal structures, resulting amorphous materials with unique properties. And mechanochemical synthesis. It supports solid state reactions between materials during the milling process that enables the formation of new compounds without high temperature processing. And in this ball milling method, no requirement of high temperature. Unlike many chemical synthesis methods, and this ball milling can be performed at room temperature itself and preserving temperature sensitive materials. Coming to the disadvantages of ball milling, contamination of the product, one of the important disadvantages of ball milling. The grinding media and the milling chamber can wear out over time. So that may potentially introduce impurities into the product. So those impurities may be the metal particles from the grinding media or the cylindrical chamber. So that is especially critical for high purity applications. And second disadvantage is energy intensive process. Ball milling can consume significant amounts of energy, particularly during extended milling periods or when using high speed mills. We need that needs more energy, so it consumes more energy. So time consuming also. Achieving nanoscale particle sizes, it may require long milling durations, several hours to sometimes it requires days, which can slow down overall productivity. And another disadvantage is agglomeration of nanoparticles. Very fine particles produced, sometimes they may tend to stick together, so they may tend to agglomerate. So that agglomeration reduces their effectiveness or requiring post treatment to disperse them. So to reduce that agglomeration, so after the preparation again we need to treat them to disperse again. So that needs time, and also it requires some chemicals, so that it is costly. So next disadvantage is limited control over shape and size distribution. While ball milling, it can reduce particle size, precise control over shape and size uniformity is often limited compared to chemical synthesis method. Of course, with ball milling method also we can have the reduced size and precise control over shape and size, but uniformity is not possible, may be possible, but it may be limited compared to the chemical synthesis method. And another important one is heat generation. Mechanical grinding generates heat. So obviously that can degrade temperature sensitive materials or influence the properties of the final product. And it is not suitable for all materials. Some soft or highly ductile materials, they may deform rather than fracture, making them difficult to process via ball milling. And these are the applications of ball milling. Nanomaterial synthesis, production of metal and metal oxide nanoparticles, fabrication of quantum dots and nanocrystalline powders is possible with the ball milling methods, and also alloy and composite formation, mechanical alloying of metals, production of metal matrix and polymer composites is possible. And third important application is it is used in pharmaceutical industry for the preparation of fine drug powders for enhanced bioavailability and mixing and blending of pharmaceutical ingredients. And fourth one is ceramics and electronics. So fabrication of ceramic materials with a fine grain structure and preparation of electronic materials like ferrites and dielectrics is possible with ball milling. Catalyst preparation. Synthesis of supported catalysts with high surface area is possible with the ball milling method, and homogeneous mixing of catalytic materials is possible with this method, and recycling and waste management is also possible with the ball milling method. Grinding of electronic waste or used batteries for material recovery, then crushing of industrial byproducts for reuse. This ball milling method is very much useful. And then chemical reactions, mechanochemistry, that is inducing solid state reactions that form new compounds without solvents is possible with this ball milling, and this is used in green chemistry and sustainable material synthesis. So these are all the various applications with the ball milling method. So thank you for watching my video. Please like, share and subscribe. Thank you so much.